Hey guys, I am doing an extra video here for one of the homework problems that you were assigned, and a lot of you guys missed class that day because you were on the New York trip. So I wanted to give you the opportunity to see the answer key, and then also if any of you need extra help with the graphs in the calculator, this is going to help you out with that. So in Chapter 3 we examined some data from a study that investigated why some people don't gain weight even when they overeat. And the thinking is that maybe some sort of extra movement, maybe people that kind of fidget, tend to not gain weight. So researchers deliberately overfed a random sample of 16 healthy young adults for 8 weeks, and they measured the fat gain in kilograms and the change in energy use in calories from activity other than the deliberate exercise that someone might partake in. So we will call the non-exercise activity NEA change, and the units are calories, and then we're going to also look at fat gain in kilograms. So we've been asked to construct and interpret a 90% confidence interval for the slope of the population regression line. So the first thing I want to do is state how we're going to accomplish this. We want to estimate the true slope beta of the population regression line relating NEA change to fat gain at the 90% confidence level. So in that state, it's really important to not only obviously say that you're going to estimate the true slope beta, but also to talk about the two quantitative variables and the fact that you're relating NEA change to fat gain, and then also mention your confidence level. So that's three important pieces of information in that one little sentence. Plan. If the conditions are met, we will use a t-interval for the slope to estimate beta. And the main thing that I want to go over with you guys today is how do you actually check those conditions. Now, in this example, we have been given data, but we have not been given a computer regression output, and we haven't been given any graphs. So we're having to do everything pretty much from scratch, and I wanted you to have to see how that's done from start to finish. So the first thing you want to do is you want to generate some graphs. You're going to create a scatter plot of your x and y variables. The second thing is to create a residual plot, and I'm going to show you how to do that. You have to run your regression. Either run option 8 under Stat Calc, or you can run the LNREG t-test or the LNREG t-interval. And for this one, we would want to run the LNREG t-interval because that's what we're trying to do here. And you must do that first because it creates what is called a residual file, and you use that for the second plot. You also use it for the third plot, which is a normal probability plot of your residuals, or a histogram of your residuals, or if one doesn't give you what not giving you the confidence that you need, then you can look at the other. Some of you may develop a preference as to one over the other as you practice this more and more. So we'll kind of look at both of those options there. So what I'm going to do is I'm going to go to my calculator. I have already put in all my data, and you can see I have my NEA change here, and I have my fat gain here. So I have everything already in my calculator the way I need it. The first thing I'm going to do is I'm going to go ahead and run LNREG t-interval. So that will be stat test, and it is, for my calculator, it's going to be option G. So I'm just going to go up, and I'm going to grab option G. Now, list 1, list 2, because that's where I put my x variable, my y variable. My confidence interval is going to be 0.9. If you would like to store your regression equation, and that way you can see your line actually graphed over your x and y scatter plot, what you're going to do is you're going to enter vars here, and you want a y variable because we're going to be entering a function, and you can put it in any of those, but I chose y1, and then I'm going to calculate. So I actually have my interval already. So here it is. But as usual, we have to actually use the formula and make sure we show all our steps for everything. A lot of this I will come back and talk about in a few minutes. Of course, we need our interval. We need our slope because that's our estimate. We need degrees of freedom. We need the standard error of our residuals. That's S here. We need our y-intercept. Not really for this, but it's important to know where that is. And then, of course, if you need r or r squared to talk about the linear relationship. Okay, so I'm going to go ahead and go into the graph. So second, y equals, we'll get into your stat plots. And I'm going to go into option 1 or graph 1, and I'm going to choose the scatter plot, and I want to make sure I have list 1 and list 2 selected. And then I can, if everything else is right, I'll just do zoom 9, and this will graph my, not only my x and y data points, but also the linear regression line that we just generated. So overall, what I'm seeing from this is that there is a moderately strong, it's an okay relationship there, strength of the relationship. It's definitely negative. It looks linear. I don't see any other form there. But I do need to look at my residual plot to make sure I'm not missing something. So far, so good addressing the linear condition. So the next thing I'm going to do is go back into my plots. And the only thing I have to change is list 2. Because I don't want x versus y now. I want x and I want it versus my residuals. So now I'm going to go in and I'm going to basically grab my residual file. It's a list. So do second stat and it pulls up your list. And you can see for me it's option 8. Now the other thing I want to do is I do want to turn off the linear function, the actual linear regression output there, because I don't want that cluttering up my residual plot. So I have everything ready, zoom 9, and it gives me a plot of my residuals. And again, looks pretty good. I don't see any pattern here. It's pretty scattered above and below. That's sort of a bigger residual, but overall, this residual plot is going to do 2 things for us. It's going to give us the ability to talk about the linear relationship because I don't see any curvature or any leftover pattern. I think that the linear form is a good fit. The other thing is I have to address the equal variance condition here. And essentially what you're looking for is remember that every x should have about the same variance. So you're really looking for a pretty even scatter above and below the y equals 0 line here. And that looks pretty good as well. So that's the second plot we're going to do. The third plot I'm going to show you, I'm going to go back into stat plot, and I need to do a normal probability plot. And it's been a while since we've done those, so I want to remind you how to do that. You go over to the far right and select that plot. And it's of our residuals. So I want to go in again and grab that residual file, option 8. And typically I do the data axis to be X. I set it that way. And zoom 9 will take care of giving us our normal probability plot. And overall, looks pretty good. Remember that what we are looking at here is our variable that we input, which was our residuals. And we're trying to see if those residuals follow the normal distribution. So it actually generates, you don't see it here, but it actually generates all the z-scores for you for the y-axis. And if it follows a normal probability, you end up with a pretty straight line here. That's essentially what we're looking for. There is something going on over here, it kind of drifts off to the right there, but overall it looks pretty decent. I might want to go ahead and do a histogram just to make sure. So then I'm going to go back in and just kind of remind you how to do that. So it's going to be the third plot over, and I already have my residual file here, and I'm just going to zoom 9, and it's going to set the window for me. And overall, even though there's a gap here, it's not perfectly symmetric. What I'm looking for here is vast departures from normality. Anything that you really see that alarms you, that makes you think, no, this could not possibly be normal. I don't see anything here. This looks pretty good to me. So I'm going to proceed to kind of writing up all my conditions now. Okay. So the first thing is linear. The scatter plot shows a clear linear pattern. Also, the residual plot shows a random scatter of points about the residual equals 0 line. So we look pretty good there. Independent. Now we're not really addressing the independent condition with any of our graphs, but you obviously need to do that. You need to make sure that your individual observations of fat gain are independent, and they should be if the study was carried out properly. And they did say that they randomly selected, so that will help with the independence. Also, because they sampled the 16, we need to make sure that we have at least 160 healthy young adults in the population, which that is obviously pretty reasonable. Okay, so we looked at both the normal probability plot of the residuals and the histogram of the residuals, and they both looked pretty good. So the histogram of the residuals is roughly symmetric and single-peaked, so there are no obvious departures from normality. We also looked at the normal probability plot, and it looked fairly straight as well. Equal variance. It's sort of hard to tell because there were only 16 observations, but it appeared that the scatter of points was pretty much consistent above and below for every x value. Okay, we already kind of talked about that. The last thing is random, and it's stated in the problem that the subjects were selected randomly, so we should be fine with that condition as well. Okay, now actually constructing our interval. So we're going to use a t-distribution with 16 minus 2 or 14 degrees of freedom to find the critical value for a 90% confidence level. Now, I want to show you how to find the 1.761 in the calculator. So I'm going to get out of this again, and I'm going to go back to my calculator. That will be inverse t. So I'm going to go into my distributions, and it's option 4. And because it's a 90%, that means I have 10% in the tails, but specifically half of that in the left tail. This is just how I do it. And then the degrees of freedom was 14, and there you go. So this is giving me obviously the left side, and then I have the positive 1.761 as well. Okay. Now, let me just kind of click through this real quick. Now, here is our slope we found earlier from running the regression. And then we have, adding to that, obviously our margin of error, which will be our critical value times standard error of the slope. So again, I'm going to kind of show you how to find that in just a second as well. I'll go ahead and conclude, and then I'll wrap up by showing you the standard error of the slope. That's probably one of the harder things. If you're not given the computer output, then you have to actually find it using the formula. So we're 90% confident that the interval that we found captures the actual slope of the population regression line, relating NEA change to fat gain for healthy young adults. Okay. Now, it's only going to be where we can inference this back to the healthy young adults, because that was our random sample. It was a random sample of 16 healthy young adults from the population of healthy young adults. So that's as far as we can take that inference. So let me go back to the calculator, and I will show you where we're going to get the information for standard error of the slope. Okay, so what I need to do is, again, I'm going to kind of just run the Lin-Reg T interval again, just kind of reminding you where we got all of our information. Okay, and in particular, I am interested in S right now, okay? So I need my S, which is going to be this value right here, 0.739852873. So, sorry about that. That is for my other class. So then I'm going to have, can't get this to turn on, but you're going to want to write down this value here, okay? The other thing I want to do is that I want to go and I want to find the actual standard deviation of my X variable. So I'm going to need to do that by running the one var stats. Okay. Now, so when I go into, remember you do stat, and then you go over to calc, and one var stats, and I just need my list 1. Frequency list should be left blank on this one. And what I'm looking for is the 257.6567. So 257.6567. And then the way that I'm going to compute this is I'm just going to use the S that we found, the standard error of the residuals, which was 0.7398. 529, I kind of rounded that a little bit, and then I'm going to divide that by, and I need the standard deviation up.